A preface acknowledgement sincere thanks to the staff at the National Reference Laboratory for Non-Ionizing Radiation, Ministry of Health, Czech Republic, especially Dr. Ludik Pekark and Ms. Dagmar Pisarikova who provided much-needed assistance with the meeting organization. The support received from the World Health Organization, the Ministry of Health, Czech Republic, the European Commission FP6 Coordination Action EMF Net, W Figure 1 Stray current wave shape in delivery cable in an office building. The peak-to-peak current is of the order 20 AE of Figure 2 the Fourier spectrum of the wave shape in Fig 1. Note the high 150 Hz component. 66. EMF hypersensitivity. Possible that a high electric field background in a room is an indication of a certain type of job, in small rooms with lots of electrical equipments. Sandstrom et al. 2003 monitored the ECG in an EHS patient group and a control group. The 24 hours Mecan and median values of the magnetic field recordings for the patient group was 0.10 and 0.05 oot, respectively, and for the control group the corresponding values were 0.11 and 0.06 oot. The mean values of the broadband field and the intermittency were also analyzed during sleeping time and when awake, and no significant differences in magnetic field values were found between the groups. Radiofrequency fields have been studied by Altpeter et al. 1995, in connection with health effects from a shortwave transmitter. He found a higher frequency of disorders of a neurovegetative nature among residents up to about 1,000 meters from the transmitter, and the 24 hours average magnetic field from measurements in the bedroom in this zone averaged to 2.5 milliamperes per meter, which was slightly higher than in the zones further away from the transmitter. A few studies have also been done of people living near base stations. Santini et al. 2002 performed a study in France and Navarro et al. 2003 did a study in Spain. None of the studies have reported how subjects were selected for participation in the studies, and participation rates cannot be estimated. Participants have answered questions about various symptoms such as headaches, concentration difficulties, memory loss, fatigue, sleeping problem, etc. They were asked to estimate the distance to the nearest base station, but it has also been shown that distance is a poor surrogate for RF exposure from base stations. Shoes and Mand 2000. In the Spanish study, measurements of the exposure in the homes were made, but did neither report how subjects were selected for measurements nor the proportion of subjects agreeing to have measurements taken in their homes. Both the French and the Spanish study report an increased prevalence of symptoms close to base stations, but the design limitations make it impossible to assess whether these findings are a result of bias or real effects. Hutter et al. 2002 studied effects on health and well-being in Austria in connection with base stations. They found a significant relation to measured power density in cardiovascular symptoms and perceptual speed. However, the study was an explorative one and no far-reaching conclusions can be drawn. All the measured values vary far below recommended levels. Max value found 1.4 milliwatts per meter, 95 percentile 0.57 milliwatts per meter. 73. EMF hypersensitivity provocation studies. It is also of interest to look at the provocation that has been done where EHS people have been exposed to EMF. Rubin et al. 2005 recently reviewed these. An extensive systematic search of databases identified relevant blind or double-blind provocation studies. The results of relevant studies were tabulated and meta-analyses were used to compare the proportions of hypersensitive and control participants able to discriminate active from sham EMF exposures. In total 31 experiments testing 725 electromagnetic ally hypersensitive participants were identified. 24 of these studies found no evidence to support the existence of a biophysical hypersensitivity, while 7 reported some supporting evidence. For 2 of these 7, the same research groups subsequently tried and failed to replicate their findings. In 3 more, the positive results appear to be statistical artifacts. The final 2 studies gave mutually incompatible results. Thus, the meta-analyses found no evidence of an improved ability to detect EMF in hypersensitive participants. The so-called TNO study examined the effects of RF signals from mobile phone base stations on cognitive functions. Zwamber et al. 2003. Cognitive functions, reaction time, memory comparison, dual tasking, visual selective and filtering irrelevant information were measured during exposure. to a 1 volt per meter field at 900 MHz and 1800 MHz GSM signal, or 2100 MHz UMTS signal. Each session took 45 minutes including exposure, questionnaire, and break. The questionnaire estimated degree of well-being from 23 assessed symptoms. Both the EHS group and the healthy volunteers reported a somewhat lower degree of well-being during UMTS exposure compared to no exposure, whereas no effects were seen for periods of GSM 900 or 1800 exposures in either of the groups. Additional studies are needed before any conclusions can be drawn. Such replication studies are ongoing in Switzerland, UK and Denmark. Discussion at present. There are no firm indications that the EMF encountered by EHS people are different in amplitude or frequency content than what is normally found in our everyday environment. However, very few studies have been conducted, but none of the provocation studies have been able to give a strong support for a connection between the EMF and the symptoms. Until we know what the interaction mechanism might be and then also know what properties of the electromagnetic field that might be of interest, further studies in this area should concentrate more of the neurophysiological findings reported on in other papers in this proceeding. Lyskov et al. 2005. 74. Physiological studies. EMF hypersensitivity, electrical hypersensitivity and tissues generating electric current, mental construction and biological reality. Jan Burz Institute of Physiology, Academy of Sciences of the Czech Republic, Prague, Czech Republic. Introduction. Unlike environmental discases due to presence of toxic or absence of vitally important substances in food, water or air, electrical and magnetic forces are indispensable for life at levels considerably exceeding the limits considered as harmful by the EHS concept. One of the underlying misunderstandings is the assumption that EMFs are novel forces introduced by technical development of industrial countries and that living creatures are not prepared to live with them. However, already the first unicellular organisms starting the evolution of life on our planet were marvelous examples of electrical engineering. Their lipid cell membrane is only 5 nanometers thick but separates an electrical potential of 0.1 volts, which corresponds to the electrical field of 10 V 5x10 M equals 2x10 volts per meter. Electrical phenomena have played an essential role in development of animals and particularly of their brains, the function of which is impossible without electrical signals mediating transmission of information between individual neurons and neural networks, and implementing the highest cognitive functions. Up to 10 neurons of the human brain generate a large amount of electrical activity, which in its diversity, intensity and ubiquity exceeds what most alleged sources can produce. Background neuron is a special cell endowed with the property of excitability, serving the purpose of intercellular communication. Kandel et al. 1999. Its main part, the cell body 10 to 100 pm in diameter, is surrounded by 5 nanometers thick lipid membrane, which separates the intracellular fluid inside from the extracellular fluid outside. The membrane is in addition equipped with ionic channels, pore-like openings in the hydrophobic wall, which allow gated movement of soluble molecules across the barrier. The intracellular fluid contains is the main cation K, whereas the main extracellular cation is Na. Difference between the ionic composition of these two compartments accounts for the membrane potential measured between an intracellular and an extracellular electrode. Under resting conditions the membrane potential is -0.07 to -0.1 volts, intracellular electrode negative, but activation of the voltage-dependent sodium channels may change 81. EMF hypersensitivity. The MP to +0.04 to +0.06 volts, intracellular electrode positive. An intracellular electrode records this so-called action potential as a transition from -0.085 to +0.05 volts, which is immediately compensated by increased conductance of potassium channels, gradual closure of sodium channels and return of the membrane potential to the resting level. The change is completed in less than 1 ms. Its full amplitude is recorded with intracellular electrode. The extracellular electrode at close distance, less than 10 pm, from the cell surface records the largest spike with the amplitude of 100 UV to IMV, which drops at 100 from the active cell to less than 10 V. The corresponding electrical field is 10 V. 10 meters equals 1 volt per meter and is rather stationary around the excited cell. In neurons with long axons, the action potential propagates far from the point where it is initiated to other neurons or effectors muscle cells. The propagation velocity is up to 100 meters per second and is marked by the traveling wave of action potential. It is obvious that the activity of this multitude of neurons, about 30 milliards in the hemispheres of the human brain, is enormous and may easily lead to disruption caused by regulation failures. This happens when all neurons are simultaneously active, e.g. during an epileptic seizure. Each action potential raises the concentration of K in extracellular space, which reaches after 5 to 10s the level of 10 mech/L and blocks further action potential generation. Such depression of activity is usually prevented by the activation of inhibitory neurons. The requirement that electrical phenomena generated in the brain tissue by external sources should not exceed the inherent level of EMF noise of biological origin seems reasonable and is generally strictly followed by hygienic regulations for the use of electrical appliances. But this is not always respected in some medical treatments, when higher stimulation intensity is deliberately used to restore a failing vital function. Thus, cardiac flutter blocking blood circulation can be stopped by high-intensity electrical pulse applied to the chest, which elicits cardiac arrest, usually followed by recovery of normal heartbeat. A less dramatic example is the cardiac pacemaker, implanted stimulator which cures patients with atrioventricular blockade by replacing the irregular discharge of the cardiac sinus node by electrical stimuli activating the heart contractions at regular intervals. The same applies to stimulation of various brain centers, which may elicit in animals pleasant feelings, motivating them to press a switch administering a short, 0.1s, electric stimulus, about 40 UA, to the hypothalamic pleasure centers. Olds and Milner, 1954. High preference of this artificial activity against other motivated behaviors, e.g., feeding, drinking, shows that the nature of the stimulus does not interfere with its further processing and does not prevent the animal to use the cognitive functions required for access to the rewarding stimulation. Similar desirable effects of brain stimulation were recently demonstrated in Parkinson patients, whose tremor, rigidity, muscle weakness 82. EMF hypersensitivity and difficult walking are clearly alleviated by self-administered series of pulses applied through implanted electrodes to their thalamic nuclei. w.h.o et al. 2003. Electrical stimulation requires application of higher voltages and currents produced by technical devices, but biological forms of effective stimulators were introduced by the evolutionary process millions years ago. Several classes of electric fish have developed so-called electric organs, in which hundreds to thousands cells are connected in series to a column in which the 0.1 volts CMF of individual cells may lead to the discharge amplitude of 100 volts to 700 volts, and by parallel connection of such columns to currents of up to 10 A. Grundfest, 1960. While the strongly electric fish, the electric cell, Electrophorus electricus, use their discharge for stunning the prey or for predator defense, the weakly electric fish use it for electrolycation. In Gnathonemus petersii, the electric organ discharges low rate of 10 volts pulses from the tail. Current flows through the electroreceptors on the anterior surface of the body, innervated by the lateral line nerves, which monitor the density of current flow through the surrounding water in the rostrocaudal direction. Any asymmetry of this density shows that the conductivity of the water was influenced by presence of some objects with higher low resistance in the vicinity of the fish. Electrosensitivity is also used by some non-electric fish like sharks, for detection of electric current in the environment, e.g. for finding live prey buried under a layer of sand. Sharks can detect electrocardiogram of such fish, remove the covering sand and eat the prey. The development of electrolycation demonstrates that evolution has tried a variety of available methods to improve the animal's capacity to locate prey, or avoid obstacles in the environment in which the animal lives, but which cannot be detected with effective use of vision or touch. Limited contact with aquatic environment did not lead to development of an analog of the lateral line system in humans. But the most important lesson we get from electric fishes is that they were not deterred by the mysterious force and used it ingeniously to their advantage. It is obvious that they do not obey the simplistic recommendations of environmentalists, prohibiting the use of high voltage and current, which would make evolution a very safe but rather ineffective process. We often hear in the heated discussions about the risk of mobile phones, that normative legislature should be highly restrictive, and eliminate all possibly dangerous effects of new technologies. This is the second misunderstanding. Biomedicine should not only eliminate dangerous EMF influences on the brain, but to use them effectively in diagnostic and therapeutic applications. The present norms are several times lower than the electrical fields existing in our body, but this does not mean that they cannot be ignored, if this will be the only way to save human lives. The evolution has convincingly demonstrated that living organisms can tolerate excessive values of voltage and current when this will give them obvious benefits. It is very difficult to 83.